Good day, Professor Darren and Tan Hongsen. Today I want to give a presentation about the measurable function. First of all, let us look at the definition of the measurable function. Given a measurable set E, we define a function f from E to the real number. We say that f is a measurable function on E if for every finite A, the set EA, which is the set of all x in E such that fx greater than A, is a measurable subset of Rn. Now let us introduce the first theorem. The first theorem states that the four statements on the beamer slide are the equivalent statement. The first one is f greater than A is measurable for every finite A. The second one says that f greater than or equal to A is measurable for every finite A. The third one says that f less than A is measurable for every finite A. And the last one is f less than or equal to A is measurable for every finite A. So this theorem tells us that we can change the form EA in the definition of the measurable function to another three form, which is f greater than or equal to A, f less than A, f less than or equal to A, and this does not affect the measurability of a function. Now let us present the proof by showing that 1 implies 2, 2 implies 3, 3 implies 4, 4 implies 1. We first assume that f greater than A is measurable for every finite A. Then we will have f greater than or equal to A is the intersection of the set f greater than A minus 1 over K. So the set on the left side is a measurable set as the countable intersection of the measurable set. Now, note that f less than A is the complement of the f greater or equal to A. Since the complement of a measurable set is measurable, this implies that f less than A is measurable. Using the fact that f less than or equal to A will equal to the intersection of the set f less than A plus 1 over K, we will have f less than or equal to A is measurable as the intersection of measurable set. Lastly, to prove 4 implies 1, we just need to note that f greater than A is the complement of the f less than or equal to A. Since the complement of the measurable set is measurable, this shows that f greater than A is measurable. Now we want to introduce some property of the measurable function. Given two measurable functions f and g, and a real number k, we will have k times f, f plus g, f times g, f over g are all measurable functions, where we assume that g is not 0 in the case of f over g. We will give the sketch of the proof. For the first case, k times f, we will use the relationship kf greater than a equal to f greater than a over k. Where we want to mention that the direction of this inequality will depends on the sign of the k. And for the second case, f plus g, we can use the relationship that f plus g greater than a equal to the union of the set f greater than q intersection with g greater than r, where q plus r must be greater than a, and also want to mention that q and r are all rational function. Okay, so since this is measurable, since the f greater than q is measurable, g greater than r is measurable, so the whole set is measurable as the union, as the countable union of the measurable set. So for the third function f times g, we first prove that f squared is measurable by showing that f squared greater than a equal to f greater than square root a union with f less than minus square root a. Since f is measurable, we have two sets on the right side are measurable, so their union is measurable, which shows that f squared is measurable. So now note that fg equal to 1/2 times f plus g squared minus f squared minus g squared. We have fg is measurable since f plus g squared, f squared, and g squared are all measurable. For the case f over g, if g is not 0, we first prove that 1 over g greater than a is measurable set. So if a is negative, we will have the set is equal to the g greater than 0 union with g less than 1 over a. So this is measurable. And if a equal to 0, we just need g be positive and less than infinity. And if a is positive, we need g to be greater than 0 and less than 1 over a. So since in all three cases, the set 1 over g greater than a is measurable set, this shows that 1 over g is measurable function, and hence f times 1 over g is measurable function. Now we want to consider the composition of the measurable function with other function. But before that, let us introduce another theorem. Let f be defined on a measurable set E. If f is measurable, then for every open set G, we will have f inverse G is measurable subset. Conversely, f is measurable if f inverse G is measurable for every open set G in Rn, and either f equal to the positive infinity or f equal to the minus infinity is measurable. So we give the sketch proof. The first direction, we first know that open set G can be written as the non-overlapping open interval AKBK. Then we will have S inverse G is the union of the F inverse AKBK, which is the union of the F greater than AK less than BK, which finally can be written as the union of the F greater than AK union with the F less than BK. Since F greater than AK and F less than BK are all measurable set, so we will have the whole union is the measurable set. Now, for the converse direction, we have that F greater than A equal to the F inverse from A to infinity union with F equal to the positive infinity. Since by our assumption, f equal to the positive infinity is measurable, and f inverse a to infinity is measurable as the inverse of the open set, so we will have the union is also measurable set. Now let us look at our theorem. Let phi be a continuous function in R, and let f be finite and measurable function in E. Then we will have phi composition with f is measurable. So since f is finite, by our last theorem, we just need to prove that for any open set G, phi composition with f inverse G is a measurable set. Now, note that phi is continuous, so we will have phi inverse G is an open set. And by last theorem, since f is measurable, so we will have f inverse composition with phi inverse G is measurable. This proves that the inverse of the phi composition with f G will equal to the f inverse composition with phi inverse G is measurable, and this completes the whole proof. To illustrate the concept of the measurable function, I have prepared an example. Define a function f from real number to real number. If x less than minus 1, less than or equal to minus 1, we define fx to be x plus 1. If x is between minus 1 and 0, fx equal to 2. And if x is non-negative, we define xx to be the x squared. And now we want to discuss the case f greater than a. So for the first case, if a less than 0, okay, let us look at the graph. If a less than 0, we would have the set f greater than a equal to the a minus 5 to infinity. For the second case, if a equal to 0, let us look at the graph again. Okay, then we will have this region. So this region is equal to the minus 5 to 0 union with the 0 to infinity. For the third case, if a is greater than 0 and less than 2, then we will have this region. The set is equal to the a minus 5 to 0 union with the square root a to infinity. And for the case a greater than or equal to 2 and less than 4, we have this region. which is equal to the a minus 5 to minus 1 union with the square root a to infinity. And lastly, if a greater than 4, we will have the set equal to the square root a to infinity. Since in all the case, the set are the union of the interval, so we will have f greater than a is measurable set. So f is also a measurable function. I want to mention that there is a non-measurable function if we assume the axiom of choice is true. We will need to use this lemma. Let E be a measurable subset with measure greater than 0. Then the set of the different d equal to x minus y, where x belongs to E, y belongs to E, contains an interval center at the origin. So we first construct a non-measurable set. We define an equivalent class, and x is equivalent to y if and only if x minus y is rational number. The equivalent class has the form ex equal to the x plus r, where r is rational number. So there is only one equivalent class contain all the rational number, and some distinct class contain the irrational number. We have uncountable class contain irrational number, since each class contain only countable number, but their union is uncountable. So using the action of choice, we choose one element from each class and construct a set E. Then the set of the different d equal to x minus y, x belongs to E, y belongs to E, does not contain 0, because we know that two elements from different class will have irrational difference, so they cannot be the same numbers. So we will, and E, the measure of E greater than 0 implies that E is not measurable. So after we have a non-measurable set E, we just need to define a characteristic function chi E, and if x in E, then chi E equal to 1. If x is not in E, then chi E equal to 0. Then the set chi E greater than 0.1 is the function, and is the set E, and E is not measurable, so chi E is not measurable function. Thank you. Here is my presentation.